Hi, and welcome to day 2 of optimization. This is our last lesson of the semester, our last lesson of pre-calc. Welcome to the finish line. This is it. So what we're going to be doing today, only really two different kinds of problems here. Number 11 and 12 are super similar. Number 13 and 14 are super similar as well. So it's going to look a lot like yesterday. Um, have to find minimum or maximum, right? We're going to draw a picture, we're going to set up the derivative, we're going to solve for the derivative when it equals 0, etc., etc. It's just this, this is how you optimize. Again, you're going to see this time and time again later on in your calc or math career. It's going to come up again in calc. So hopefully this is, giving you a good, nice introduction to, to what you're going to be seeing here. And let's just do this. Let's dive into number 11, starting by reading it. I have the picture over here to the right already ready to go, but let's go into the description first. So engineers are designing a box-shaped aquarium with a square bottom and an open top. The aquarium must hold 256 cubic feet of water. What dimensions should they use to create an acceptable aquarium with the least amount of glass? Now, so I'm going to be, well, first off, say it's asking for the least here, right? Least amount, meaning a minimum, a minima, however you want to say it. And then it's also talking about, right, this box-shaped aquarium with a square bottom and an open top. Now, according to my picture over here, and you should draw this, okay? Draw this over here, is I have a box-shaped aquarium, which this is box-shaped. It has a square bottom. Now, that's key. So my length times width is a square, okay? And then obviously there's a height as well, right? To a box, that's usually what our volume is. We're talking about volume here. Why? Because in the next sentence it says 256 cubic feet. So this is referring to the volume of the box. It has an open top, so only 5 faces, not 6. Now I'm going to adjust kind of the information we're given here in accordance to volume. Volume is usually our length times width times height, right? So L times W times H would be our usual formula here. But according to the square bottom part of this, right, the square bottom, that means length and width are equal. Okay, so length and width, we can represent those as the same variable. I'm just going to use x here, and I'm going to write x squared, okay, because it's x times x, right? And then times our height, which I'm going to use y for our height here. So that's kind of our adjusted volume here. I hope that makes sense because the length and the width are the same, right? It's a square bottom. Now we can also go one step further as saying the volume is 256, then that equals the x squared y. Okay, so that would be our first known equation, right? We're after this known equation and this unknown equation. Well, this would be our known equation. Now, our second equation, or our unknown, what is our unknown? Well, it's this part, this last sentence, is what dimension should they use to create an acceptable aquarium with the least amount of glass? Now, it's referring to the surface area there, right? It's the surface area of the aquarium, and we know what surface area is, and I am going to represent that as SA, okay? But what is the equation of our surface area of this aquarium? Well, there are 5 faces here, right? The open top is, there's no face on the open top. That means there's this left side, this back side, this right side, and this bottom one, and the front one. So we have 5 faces there, and there's 4 faces that are x times y, and then there's that bottom face, which is just x squared. Now, I do want to take some time to adjust this photo, or this picture, is we said the length and the width are the same, so we represented them as the same variable as well. So here's my x, and then here's my y for the height. Okay, and I hope the surface area now makes sense, right? We have 4 faces that are x times y, right, and then this front face. And then we have this bottom face that's x times x. Okay, so we have 4 x times y's, and then we have the x squared. So that's where that surface area equation comes from. We have our known now, and we have our unknown. So from yesterday, what we want to do is get that known equation and plug it into our unknown to get that unknown equation in terms of the same variable, or that there's one variable in the equation. Now, what we're going to do is just adjust that known one. So this known equation is just going to adjust to y equals 256 over x squared. Now, I just divided the x squared there on each side. I hope that makes sense. But we want to do that so we can substitute in to our unknown. Okay, hopefully this is sounding familiar from yesterday. So SA is now going to equal 4x times our new y. Our new y is the 256 over x squared plus x squared. Okay, now that we have that, we have to do a little bit of simplifying before we can get into taking our derivative. So hopefully you see what's going to happen already is that 4x is going to combine in onto the top, right? We could really write this over 1, do that if necessary. We're getting 1024 over x squared. Sorry, 1024x over x squared, right? 4x times 256, then plus x squared. Okay, and I don't think I want to use or find the derivative yet here. I think I'm going to simplify even more. So let's do this. Let's take out an x here. We're left with an x on the bottom. If there's an x on the bottom, I'm actually going to spend the time in taking it and moving it to the top. So if the x is in the denominator, it's now in the numerator, and that means there's going to be a -1 exponent on there. Okay, and I'll show you why we're doing that, because the derivative is going to be much easier to take now with that x to the negative first. Okay, and the derivative is going to be, right, if we just use the power rule, okay, use that power rule. Actually, this would be a good time to pause it and use that power rule. But the power rule is going to get us -1024 x to the -2 plus 2x. Okay, so that is the derivative of the surface area, right? This is what we're doing. We're taking that derivative so we can find the minimum and maximum. Here, minimum, right? So there's our derivative of our surface area. Now I am going to adjust this a little bit, though. So I'm going to go up here to the top, and I'm going to rewrite that derivative because I think it's going to be easier to set it equal to 0 if it's in a different way, if it's written in a different form. And all I'm going to do is take that x and move it to the bottom. So -1024 over x squared. Now that squared is positive plus the 2x. Okay, we have the derivative in a nice form now, and it's going to be easier to find what x is, or when the derivative equals 0, when we have it in this form. So let's set it equal to 0. We're not going to find where it's undefined, because I'll tell you right now, it's not going to be defined any time this function isn't. So we don't have to worry about that. And it's not going to be undefined throughout any of these, so we don't have to worry about that at all. What I'm going to do here, though, since we've set it equal to 0, is then subtract it by 2x here. Okay, and I'll show you why. We get -2x equals -1024 over x squared. Now, the reason we did that is because it's going to be easier to take, or to solve for x. Now, we can really throw this -2x over 1, and then we can just use our friendly cross multiplication to get x. So let's do that. We're taking -2x times x squared, and then 1 times -1024. So oh, I wanted green there. We have -2x to the third then equals -1024. Okay, well, I'm going to divide by -2 here. Divide by -2. We're getting x cubed equals 512. Now, we still don't have x alone, okay? But what we need to do here is, I hope you see it, is take the cube root of both sides. Cube root, Okay, you can do that in your calculator. If you know your cube roots by heart, then good. This should be x equals, sorry, just had the wrong color there. X equals 8. So the cube root of 512 is 8. And then the last thing to do, we have the length and width, right? We have our x value. Then we got to find our y value, or our height. So let's do this. Let's take our known adjusted volume and just plug in x, right? Because it's already set as y equals. So let's do that. And we're going to get y equals 256 over x squared, which is really 8 squared, which is 64. Y equals then 4. So we have 8 by 8 by 4 is our dimensions of the aquarium, is the minimum, dimensions of the aquarium to hold the 256 cubic feet of water. So 8 by 8 by 4 feet. Don't forget the feet, because we are talking about cubic feet of water here. So that's the dimensions of the aquarium to hold the 256 cubic feet of water. Now, number 12, moving in, is super, super similar. It's the same exact thing. And we actually have the same picture here. Is I'm going to label it as XXY, okay? And then when going into finding our known equation, well, we're talking about 108 cubic feet of water this time. All right, and we're still minimizing, we're still finding the least amount of glass used for the surface area. So let's do this. Let's write our known and our unknown. Our known is the volume, 108 equals x squared times y. Okay, I'm not going to spend too much time on the explanation there because we did it up here. Same volume. Our surface area is the same as well. So surface area is going to be those 4 faces of x and y, plus that last 5th face, or the bottom, which is the square bottom, x times x, or x squared. Now, let's adjust our known to get it in terms of y equals, right, 108 over x squared, because we need to substitute that into our unknown and have that in the same, in terms of one variable. So we have y equals 108 over x squared. Let's adjust our unknown here, so it's in terms of one variable. 4x times 108 over x squared. Again, if you want to just pause this and try this one out, it's super similar. We got the same looking setup here. Let's distribute the 4x in. Okay, so surface area is going to equal 432x over x squared plus x squared. It looks like we can cancel some x's here. Let's do that. Cancel those. Let's also move that x in the denominator up to the top. Okay, so 432 x to the negative first plus x squared. Okay, that's in a form we can take the derivative a little bit nicer. So let's do that. Use the power rule here. Pause it especially to get this one. Just to remind yourself of the power rule. Bring down that negative. And then we have x to the negative 2 plus 2x. Okay. You're going to call me crazy, but move that x back down, okay? And because that's going to be a lot easier for us to find x, or where the derivative is 0. So negative 432 over x squared plus 2x. Okay, and then I'm going to go up here. Let's set it equal to 0. 0 equals negative 432 over x squared plus 2x. We're going to subtract that 2x over, so negative 2x equals negative 432 over x squared. Now throw that negative 2x over 1 so we can cross multiply and solve for x. So we're getting negative 2x times x squared, and we're getting 1 times the negative 432. I'm going to keep my x term on the left side, so negative 2x to the third equals negative 432. Okay, couple more steps to go. right? We need to divide by -2 here, divide by -2. We're getting x cubed equals 216. Now, if you don't know your cube roots here, do it on the calculator. We're going to take the cube root of both sides, cube root, and x is going to be, ding, 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 6. So there's the length or width, well, length and width of our aquarium. Okay, now let's take our adjusted volume and get that height. Okay, y equals 108 over that 6 squared. Okay, you can do that on your calculator quick. You should get y equals 3. Right, 108 over 36 is 3. Good, yep, that's right. And then our dimensions then now is the 6 by 6 by 3 feet. We're still in cubic feet here, so our surface area is in feet as well. So those are our dimensions of the aquarium in number 12. So again, these were really similar, in fact, right? Number 11 and number 12. Hopefully the explanation went okay for you there. A little bit of writing, but not much different from unit 11 when, you know, getting the derivative, finding where the derivative is equal to 0 or undefined. In this case, no undefined here, just where it's equal to 0, and then finding that minimum or maximum. In this case, these last two, they were both minimums. So there's the dimension there of number 12. So let's go into 13 and 14. Now, 13 and 14 are both problems that involve revenue or income, however you want to say it. We're going to go with revenue because 13, it actually says revenue. So this is talking about revenue. Now, revenue of something in a product is really, right, the product, the number of product or the quantity times the cost of the product, right? So what I like saying is this is a quantity cost problem. And, sorry, it's a quantity cost problem. And we got to set that up. Now let's first, oh my gosh, what's going on? Let's start by reading it. So the regular airfare between Boston and San Francisco is $500. An airline using planes with a capacity of 300 passengers on this route observes that they fly with an average of 180 passengers. Market research tells the airline's manager that each $5 fare reduction would attract on average 3 more passengers for each flight. How should they set the fare to maximize their revenue? Explain your reasoning to receive credit. Now, again, we're talking about cost and quantity, right? And the cost is going to be the fare price, right? This fare price. And the quantity is the number of passengers, right? So I don't know where it says passengers here. 300 passengers, right? Or 180 passengers. So that is our cost and our quantity here. So let's set up what our revenue is really going to be. Well, it's going to be the revenue equals the fare times the number of passengers, right? That's just what I said. The cost times the quantity, right? The number of passengers. So that is really going to be what our revenue is. But there's something that's affecting our revenue in a way. It's affecting our fare and our number of passengers too. So, right, the number of reductions that this market research or whatever tells us, okay, and I will tell you, since that is affecting our revenue, that is going to be what we're going to take with respect to R. And so our X here, well, I'm just going to write it. Our X here is going to represent number of reductions. So X equals number of reductions. Okay, well, how does that number of reductions affect our fare? Well, let's go back and read. Our airfare between Boston and San Francisco starts at $500. Now, after a reduction, $5 is taken away, and that's per reduction. So our equation is now going to be R of X, right, with respect to X, or the number of reductions, is going to be $500, right? The $500 minus the $5 per reduction. So that makes, this part makes sense, right? The $500 minus the $5 per reduction. And then our passengers is affected by the number of reductions because on average, after the 180 are on there, 3 more passengers are added to the flight. So this part, the number of passengers is affected by the reductions because 180 plus 3 more passengers times the number of reductions. Okay, so that's how the reductions are affecting the fare and the number of passengers. And hopefully you can see that is the reason why this revenue is going to be, maximized. Okay, so we're going to be looking especially at this second equation here, and we're going to be using the same method. We're going to just find the derivative, find the maximum, and then it says how should they set the fare to maximize their revenue, and then explain our reasoning to receive the credit. So let's do this from that equation. How do we want to take the derivative here? Do we want to take the product rule? I don't think so. What I think we should do, and this is what we will do, is multiply through those parentheses. So the 500 times the 180, that's 90,000. Again, you could do this on your calculator. 500 times 3x, well, that's 1500x. 1500x. And then we have 5x times 180, that's minus 900x. And then we have minus 15x squared. Okay, so let's go one step further. Let's combine here. You should get that. I just combined the two middle terms. Now let's take the derivative, right? So we're still in the same process of finding the minimum or maximum, in this case maximum. So we got to take the derivative and then set that equal to 0, or find where the derivative is 0. Now what's the derivative of 90,000 plus 600x minus 15x squared? Well, 90,000 is just 0, and then we have 600, right? This is again the power rule. So pause this and try this one if you want. And then the derivative of negative 15x squared, well, that's negative 30x. Let's set that equal to 0. Okay. Same method here. We're just going to add over that 30x. We get x equals 20. Okay, so remember, x is the number of reductions. So we just found the number of reductions that market research is influencing, or telling us that it's going to maximize our revenue. So the number of reductions the airline should make is 20. Now it also, let's go into let's also figure out how many, how much the fare is going to be. Well, the fare is 500 minus 5x, the number of reductions. Well, our number of reductions, the market research just allowed us to figure out, was that there should be 20 reductions taken in order to maximize their revenue. So let's plug in that 20, and it looks like we're getting $400 per ticket. So the airlines company should make 20 reductions, and when they do that, the maximum price of the ticket will be $400 in order to maximize their revenue. So let's just put that in terms of words here. And this is kind of what I came up with, and I'm kind of just repeating our knowledge that we figured out in really Unit 11. So $400 per ticket maximizes their revenue, because where the derivative of the revenue function is 0 is the maxima of the function. So again, just knowledge that I'm taking from Unit 11, but putting it down in words. And it does ask you to do this, so explain your reasoning. Make sure you read these directions. But yeah, so the number of reductions, 20, and then the fare per ticket would then be $400. So that's a cost and quantity example. Now, in number 14, we're going to do the exact same thing, because we see another cost and quantity equation. Now, let's read this one, carefully here, because there is one thing I want to point out that if you don't read carefully enough, you might miss. So a Florida citrus grower estimates that if 60 orange trees are planted, the average yield per tree will be 400 oranges. The average yield will decrease by 4 oranges per tree for each additional tree planted on the same acreage. How many trees should the grower plant to maximize the total yield? So again, a cost versus quantity problem, but really not cost, because our cost is, we're talking about you know, oranges per tree. So I think what I'm going to write here instead is just a little bit adjusted, but not much. I'm going to use Y, capital Y, as total yield. Okay. And we'll use with respect to X, but it's going to be just how many times how much. Okay, and that's kind of my adjusted cost and quantity equation. But I did want to go a little further than that. The reason why I'm using capital Y here is because total yield. Okay, Y is going to be total yield, right? And there is a difference between average yield and total yield. Okay, so those are two completely different things. That was the first thing I mentioned here, is that if you miss that, it's going to be, you know, harder to do this one. But the average yield per tree and the total yield of the farm is different here. So make sure you know that going into this one. And I did formally write this one out, or type this one out further, is I have this. So I have that capital Y equals X times A. All right, my Y is the total yield. X is going to be number of trees. A is the average yield. Okay, so again, this part right here, the X and A, is the how many and the how much. Okay, and so if you want to write something like this, go ahead. You don't have to. But this is kind of formally how I wrote it, and just defining our variables. But from what we wrote there in black, I mean, it's going to be enough for us to figure this out. So total yield with respect to X. Well, what is X? Well, that's going to be number of trees. Okay, so let's write that down. X, number of trees. And then let's figure out how the number of trees affects our total yield. So Y of X is going to equal, well, how many? So how many oranges? Okay, it says the average yield per tree is 400. So 400, but then per tree that is added, right, per tree, 4 oranges, there's a decrease of 4 oranges. So minus 4x. Okay. Well, how many trees, though? How many trees? Well, we started with 60. Okay, so this then would be 60 plus the additional trees we're going to decide on planting, okay, to maximize our total yield. So I hope this makes sense. This is oranges, right? And then how much? Well, that's the number of trees. So hopefully this one makes sense. Again, it's really similar, cost quantity. In this case, our cost is the number of oranges, okay? But let's go further here. Again, same steps as before. We're just gonna distribute through here, and then we're gonna find the derivative with when it's equal to 0, right? So 24,000 plus 400x minus 240x minus 4x squared. Okay, so we just distributed that through. Maybe I should show these here. We distributed through. Let's combine like terms. 24,000, and then that's that's plus, right? Plus 160. Yeah, 160, and then minus 4x squared. Okay, time to take the derivative. Now we're taking the derivative of the total yield. So change that notation, make sure that notation is right. Derivative of 24,000 is 0. Derivative of 160x is 160 minus 8x, right? We're just using the power rule there. Well, let's set this now equal to 0. 0 equals 160 minus 8x squared, right? Let's add the 8x over, equals 160. Why did I write x squared? Okay, there's no x squared there. We had the 8 though. Let's back up. So the derivative of 160 minus 8x, sorry about that. Let's set this equal to 0. We're adding the 8x over. We're dividing by 8. X equals 20. So what that is telling us is we need to add 20 more trees, right, to our farm to get our total maximum yield. So we started with 60 trees. We're adding 20 more. So 80 trees total. 80 trees total should be planted. But it doesn't necessarily, it doesn't ask us actually, is it the total number of trees or the total number of new trees, but it is 20 new trees then, just to make that distinction. Whatever you want to write is good with us. So just read carefully what it's asking here. How many trees should the grower plant to maximize the total yield? Well, 20 new ones and then 80 total. So that's how number 14 goes. Not too difficult here. I think 13 and 14 were actually pretty much easier or less work than the first two. So hopefully that makes sense. Hopefully cost quantity now makes sense to you guys and how derivative applies to finding maximum and minimum. This is pretty prevalent stuff. I mean, when you're talking about revenue, we all love money. We want to know how to maximize it. So that's where, this is where all this kind of stuff and knowledge is coming into play, is in these applications. So hopefully that went well for you guys. Again, this is the last lesson of the year. So hopefully this went well for you guys. Hopefully it was a good semester as well. It was a pleasure speaking with you guys, talking with you guys, teaching you guys, assisting you guys. I really want to say thanks. It was a great time. Hopefully you enjoyed it too. So again, if you have questions about this, I'm here, Miss Vasquez, Miss Weedoff. I'm always happy to help. But we're signing off here. This is the last one. So we'll talk to you guys later, hopefully. Otherwise, good luck the rest of the way. Hopefully this semester prepared you for what's coming in calculus. Okay, so thanks, and we'll see you.